Hello and welcome to lesson 18 of this Introduction to Calculus with Wolfram U. The topic of this lesson is derivatives and the shapes of graphs. So let's begin with an overview of the lesson. So in the last lesson we spoke about the mean value theorem, and you might have got just a hint as to how powerful this theorem is. But in this lesson we'll actually see that power in action, and we'll actually learn how the derivative of a function can be used to sketch its graph. That's a very beautiful application of all the calculus ideas we've learned so far. So, for example, here's the function f of x equal to x squared, and that's the derivative of the function. Now, the function itself, of course, is just a parabola in terms of its graph, and the derivative is a straight line graph. And the point is that starting from this derivative, you can actually plot the original function. And that's the theme of this lesson. The goal of this lesson is to develop a way for sketching such graphs. So let's begin by building some intuition. So let's again look at the graphs of x squared and its derivative. So we have the function on the right, the derivative on the left. And you see that when x is negative, the derivative is negative, and that says that the function is decreasing. And when x is positive, the derivative is positive, and that says that the function is increasing. And finally, when x is 0, the derivative is 0, and that says that the function is horizontal just at that point. So with that background, we can now talk about the increasing and decreasing function test. But let's begin with the mean value theorem, which says that f of b minus f of a is f prime c times b minus a for some value c between a and b and a. So if f prime c happens to be positive for all c, then assuming that b minus a is positive, so b is greater than a, then we have f of b greater than f of a, so the function is increasing on that interval. So using the mean value theorem, you can show that if the derivative is positive, then the function is increasing. And in just the same way, if the derivative is negative, then the function is decreasing on that interval. And these two facts together are called the increasing decreasing test. So as an example, here is the plot for x cubed and its derivative. And you see that the function is increasing everywhere. And if you look at f prime, the derivative, then it is non-negative at all points. So the function is increasing everywhere except at 0, where it is horizontal. And that's what you see from looking at the derivative for the function. So the derivative of function tells you where the function increases or decreases. So now as an example, here is a cubic function, and we want to find out where it increases or decreases without actually plotting the function. So the first step, let's find where the derivative is 0, and you find that it's 0 when x is either negative 2 or positive 1. In other words, we now know that the graph must be horizontal at those two values of x. So what we do is we break the whole real line up into three parts. The part from negative infinity to negative 2, then from negative 2 to 1, and then 1 to infinity. And now you pick a typical point in each of these intervals. So you pick, let's say, negative 3 in the first case, 0 in the second case, and 2 in the third case. So negative 3 lies between negative infinity, negative 2, etc. And work out derivatives, and you find that at the first point, the derivative is positive, and so it is at the third point as well, while at the second point is negative. And that says that the function is increasing on the first interval and the third interval, and it's decreasing on the second interval. So here's a plot of the derivative and the function, and you see over here that the orange graph is the function itself. So when the function increases, the derivative is going to be positive. When the function decreases, the derivative dips down below the x-axis, and then when it increases again, the derivative becomes positive. So that says that the derivative gives you pretty good information about the increasing or decreasing nature of a function. Okay, so how about maxima and minima? So let's talk about maxima and minima and look again at the earlier function. You see it's got a maximum over here at -2 and a minimum at 1. And they are both local maxima and minima. But what you notice is that when x is -2, the derivative goes from being positive to being negative. So it's positive initially, then becomes negative. And just the opposite happens at the minimum, where the derivative is first negative and then positive. Now, if you look on the other hand, the graph of x cubed, then you see over here that the derivative does not change sign as you go through 0. So that says that you do not have a local maximum or minimum roughly. Okay, so now we can talk about the first derivative test, which says that if the first derivative changes from positive to negative at a point, then that point has a local maximum for the function, and just the opposite happens at a local minimum, where the derivative changes from being negative to being positive. And on the other hand, if the derivative does not change sign at a point, then the function neither has a local maximum or a minimum at that point. So as an example, look at the sine function and its derivative, which is just the cosine function. So here's the sine function. And you see over here that you have a maximum at pi/2, and the derivative goes from being positive to being negative. And on the other hand, you have a minimum at 3 pi/2, and the derivative goes from being negative to being positive. Okay, so that's about first derivatives. And how about second derivatives? So here is the graph of x cubed and its second derivative, which is 6x. So you see over here that when the second derivative is negative, the slope becomes progressively smaller. It slows down, so to speak, the function. And when the second derivative is positive, the slope progressively gets bigger. You can see that over here. So in the first case, we'd say that the curve is concave downward. And the second case is concave upward. So it's concave downward over here and concave upward over there. As another example, let's look at the sine function and its second derivative. And you see over here that it's concave downward when the second derivative is negative and concave upward when the second derivative is positive. So now we can put all that together and talk about the concavity test, which says that if the second derivative is positive on an interval, then the graph is concave upward. The short form for that is cup. It's like a cup of water. And if the second derivative is negative, then the graph is concave downward. That's like a frown. It cannot hold any water in it. And so that's a nice test for concavity. Another way of looking at it is to look at tangent lines. So here's a function, x squared, and the second derivative is 2, which is positive. So you see over here that all the tangent lines lie below the graph when you have a concave upward graph. So all the tangent lines lie below in this case, and if it happened to be concave downward, then of course all the tangent lines will lie above the curve. Okay, so now on to inflection points, where you neither have concave upward or concave downward just at that point. So in fact, the curve will switch from being concave upward to being concave downward at an inflection point. So here's an example of such a function where you have an inflection point at 1 roughly. So you have concave downward over here and concave upward over there. Now what's happening over here is that the slope will reach a maximum or a minimum value at a point of this type where you have an inflection point. And so the slope is of course a derivative, and hence the inflection points are precisely those where the second derivative is either 0 or not defined. So in the case of this function over here, let's just check what happens if you set the second derivative to be 0 and solve for x. And you find that at x equal to 1, you actually have an inflection point. Okay, and finally, let's talk about the second derivative test, which says that if you have a critical point and the second derivative is positive, then the function has a local minimum. And if it's negative, so second derivative, then you have a local maximum. So looking again at the earlier function, you see over here that when you add 0, then you have the slope is 0 and the graph is concave downward, so you have a local maximum, and just the reverse happens at 2 where you have a local minimum. So that's how the second derivative is quite a powerful tool for distinguishing between a maximum and a minimum. And it's time to summarize. We learned quite a lot in this lesson. So first of all, learn that the mean value theorem is crucial for understanding how to graph a function starting from its derivative. So we learned about the increasing decreasing test for when a function increases or decreases. We learned the first derivative test for finding local maxima and minima. We talked about the concavity test for figuring out when the function is concave upward or downward, and that relies on the second derivative. We spoke about inflection points where the curve kind of changes shape. And finally, the second derivative test tells us that you can use the first and the second derivatives together to find the local maxima and minima. So that's the end of this lesson, and the next lesson we'll talk about limits at infinity and horizontal asymptotes. But before doing that, do review this lesson, do look at the exercises, and make sure you follow this topic really well before you begin the next lesson. Thank you very much. I'll stop here.